What I want to share with you is a little bit about using management plans, and particularly nutrient management plan development in practice, and starting to identify what practices make the most sense in what area. And I kind of built this presentation around two questions that I get frequently asked, and a couple that keep me up at night at times. And that is the question from the farmer, this audience that you often have, and that is relationship to what practices should I be implementing out on the farm, what makes the most sound economic decision for me to invest my dollars in relationship to making practices work. And then the second question comes when I get to talk in front of audiences that have non-agricultural folks in it. And those folks are asking the question of, well, beyond when are you going to get this accomplished? They're asking, you know, you're spending $90 million, $100 million, I mean, whatever $1 million that you want to put in front of that value in practices and working towards solutions to this problem. Are you being cost effective? How are my dollars working? And really that ties back into the farmer's decision as well, as far as are these dollars that we're spending on practice implementation cost effective, and are they getting us towards the goal that we're trying to accomplish, and that is reducing phosphorus by 40%. I want to kind of divided up the session here in two ways this morning. I wanted to talk a little bit about what are P reduction goals. It's been mentioned a couple times, 40% reduction, 40% reduction. Well, you know, percentages are sometimes hard to deal with, and sometimes real numbers are better to put focus on what we need to try and accomplish. And so I put a few real numbers to that 40% and help maybe understand what the breadth of the problem is. And then want to talk about nutrient management plans and how we're starting to utilize with those nutrient management plans the results to make decisions on the farm. So this is the goal, and I got a blow up of this, but let me spend just a minute on this. And that is that we're going to see if it goes down or what we're trying to accomplish is a 40% reduction, but what the Annex 4 is doing is putting some specific targets on that as far as what is allowed in relationship to, or what target levels we want to try and attain. And let me just go ahead and go to the larger one. For the spring period on the Maumee River, what we're looking at is really total loading of 860 metric tons of nutrient going down as far as total phosphorus load, and that spring period is March through July. That time frame really correlates back to the amount of bloom or growth that we see on the lake. And then thinking about the dissolved reactive portion of that, what target would be there for that, and it's 186 metric tons is what the target is in relationship to that particular component of phosphorus. The values that you see there are to meet 90% of the time. Well, let me back up. Meeting this 90% of the time for both time-based and interannual flows. But the big thing here is it's based off of 2008 as a year that they're targeting off of, and that was a year where we had a mild bloom on Lake Erie, and that is the mild bloom that they're trying to attain consistently over time is what they're attempting to do. So any of that 40% target, I want you to know realistically it's not to eliminate harmful algal blooms on Lake Erie. It is to reduce those algal blooms to a level that would be acceptable to the public. So there's going to be an algae bloom necessarily most years, but there is going to be a reduction in years based off of those 2008 numbers. It includes numbers for other Western Basin tributaries, and that would include the Detroit River, that includes the Sandusky, and all of those are looking at a 40% reduction as well, but they don't define that target level as closely. There's also, for the overall lake health, the annual target loading of phosphorus going into the lake period of about 6,000 metric tons in relationship to that. The Annex 4 that information comes off of the report, I mean, if you have any interest at all, it's a good place to go look real quickly and see what's being defined as the problem. And the values are divided up by watershed, and looking at the contributions from watersheds, and here we're focusing in on the Maumee River and the Detroit River. And just by the pie graph, you can see that there's dramatically different sources from those two watersheds. The blue value that you see there is what's called monitored non-point sources. In other words, that's some of the river monitoring that's going on in relationship to trying to understand the watershed level. The red bar that you see on the Maumee River side, that's about, and for, well, they don't have percentages, but we do on the next graphic here, but you can just see that it has a large contribution from the blue and the red, which adds up to the non-point source total. That green slice and the purple slice is what's contributed to point sources. So you can see it's a fairly small amount that's being contributed from point sources in the Maumee River, versus when you start looking at the Detroit River, what's the biggest slice of the pie there? Yeah, it's actually the Detroit wastewater treatment plant is actually the biggest part of that pie, and they've been working on that as far as improvements there. And you can see then the unmonitored and the monitored non-point sources are really don't even add up to that wastewater treatment plant outflow. So watersheds have different sources is I think one lesson that I wanted to use in presenting this slide. This is where I try and put values on those numbers, and this is where we're talking about the 2008 loadings, and we have actually across the top here what period we're working in as far as water year, spring total phosphorus, or spring dissolved reactive phosphorus. This is what the 2008 loading was. This is what that reduced 40% target value is. This is what that reduction then would represent in metric tons, and I don't know how to represent a metric ton. I'm used to working in U.S. tons. So we convert it over to U.S. tons in the column here, and finally convert that into pounds, because I think from both Kevin's presentation and Libby's presentation, what do you get as far as an average acre, and what's it contributing as far as pounds of total loading going into the whatever watershed we're talking about? Is it hundreds of pounds? Is it tens of pounds? It's tens of pounds, and actually less than tens of pounds, really. It's pounds or two that we're generally seeing. And so thinking about it that way, I think, helps me put a better perspective on what we're trying to accomplish, and we'll use that later to judge these practices. But basically, what you boil down to is that we're looking at trying to reduce spring DRP loading 272,000 pounds. Sounds real easy, doesn't it, when you put it in that perspective? But it's not real hard, or it's not real easy to make that kind of reduction level, because we can't do it on a one-to-one basis. It's not changing 1 pound of added to the soil profile to come up with that type of a change. When we talk about the spring total loading, we're talking about 1.3 million pounds of reduction in relationship to meeting that target level. We've met those target levels in certain years, like 2016 and 2012, and what's led to those targets being met? Drought. Yeah, dry weather really helps us meet those targets, but it's not very fun times back on the up the watershed where we're trying to produce agricultural crops. I haven't gone back and looked at the 2008 year, but I certainly do want to go back and look at what 2008 weather conditions were, so that we can start putting things into perspective as far as what our target is. In other words, in a similar type of year, what we're trying to do is reduce to these target levels, and higher or lower precipitation is going to affect what that outcome is. Another important thing that I want to point out here on the graphic, and I should have made that bigger when I was adjusting everything this morning, seeing the size of the screen, but we've been talking a little bit about mean concentrations. during the day. And actually, the mean concentration target that's used for DRP going out of the Maumee River would be a target of 0.05 parts per million. Kevin had that up on his graphic, at least one of them, looking at DRP. And that type of level of concentration gets us to these reductions in overall values that we're measuring in pounds per acre. So we can look at it that way as well. Just know that this Annex 4 is being followed through on. It was adopted a year ago in February of, almost to the day, February of 2016 by the U.S. and Canada, including Ohio, in relationship to adopting these standards and start working towards management practices and implementation strategies. The thing that you want to note here is that there is a domestic action plan, which is basically what the state of Ohio is currently working on to come up with the action plan that leads to that 40% reduction from the state of Ohio. And by a year from now, that plan is going to be out. So I think we need to continue to be a part of that conversation and continue to be working with EPA, who's providing the leadership to that development, so that we understand what agricultural concerns are being addressed and what targets are being placed in there from an agricultural standpoint. One study that's kind of a part of getting to that domestic action plan is that EPA did a mass balance study. Kevin did it on a field-by-field basis if you were in here earlier as far as looking at inputs and outputs. They did this mass balance study on a watershed basis, actually for several watersheds here in the state of Ohio. What you see in front of you is the numbers for the Maumee Basin as far as that EPA mass balance study. Here, a little easier to see, the non-point source is the red. On the top, we have the total phosphorus, and on the bottom is the total nitrogen. It's broken down beyond non-point source to home sewer treatment systems, is what HSTS is representing with the blue, darker blue, and then those permitted facilities is the lighter blue. I know you can't in the back, and I can hardly read it from this angle, but when you look at total phosphorus, what's being attributed to non-point sources in the Maumee Basin? About 89%, isn't it? So kind of looks like some of those numbers that we were just looking at previously. So I think, the bottom line from this graphic as far as, looking at reductions, who's going to be looked at to try and provide the bulk of this reduction that we're seeing targeted. It's us folks in this room as probably a big part of that non-point source, just from the land base that we have out in that western Lake Erie Basin. So I just want you to see that there is a lot of work going on behind the scenes in relationship to trying to better understand this. And this is a question I'll often get asked by an audience. Well, what about the sewer treatment plants? What about the home sewer treatment? And here's at least one source that tries to account for those two different sources.
Okay, I'm just curious, where do you get the information on the wastewater plants?
The wastewater treatment plant information would come from EPA monitoring and from the permitting process that they go through. This report is online. Actually, it shouldn't say Annex 4 there. What you'll want to do is go into Google and type in EPA Mass Balance Study, and you can take a look at the whole documentation and any details as far as how it was actually put together.
Okay, well, my point to that is I used to be a councilman for a local community that had their own wastewater treatment plant. And in their permit, they're allowed 10 maintenance days. So in my community, when we got a 3.5-inch rain one day and everybody's fields were flooded and the wastewater plant was shutting the gates down, sewage blowing everybody's basements, I got the report because I was an elected official. And on the report to the EPA, we declared that a maintenance day that we didn't have to report. Now in the permit, maintenance day says a day to repair a defect. So if we have communities that have learned the loophole of not having to report an overflow and call it a maintenance day, because I'm tired of hearing all this, well, they're operating under their permit. Who checks to make sure? Because
Well,
they self-report. I mean, I grilled my public service director. He did not like the fact that I could pinpoint that little gray area that they use. We use them too. Don't misunderstand me. I'm not being super critical of wastewater plants. My point is, when we produce information to make decisions, they ought to be, EPA must know this happens. They're not stupid either. Produce accurate information so we can make the decision.
Well, in 100% agreement, the more accurate we can make this information, and still the number one question that we've never identified is what the actual source or sources of these DRP flows are, and that still is an overlying question. That it's much easier to solve a problem that you know what the problem is, and we still haven't done a good job of identifying that. But when those types of things are known, I think it's 100% our responsibility to push EPA and those that do provide that oversight to these different outflows to understand and get that accurate information and make it as possible, or as much as possible, accurate representation of what's going on out in the landscape. No doubt about that. But I wouldn't, like I said, both of those report, the Annex 4 report, the mass balance report, they're actually a lot of graphics and pretty easy to go through and provide a good basis, I think, to try and understand the problem better. And this is understanding from a watershed standpoint. This is really not trying to identify any particular one organization or group to go after. With that, what we want to do is shift into talking a little bit about a nutrient management plan and what that accomplishes for us. It certainly is a tool that provides us crop response information as far as making sure that we do have the nutrient that we need in relationship to providing the crop needs or proving the crop needs. And then secondarily wants to get involved in the assessment process as far as a field-by-field basis of understanding where we might see higher contributions and what we might target as far as getting to a better outcome. I'm going to skip a couple slides since we're running a little short on time, and I want to go back or just talk a little bit. We have nutrient management plans that at least one option to put them together for NRCS programs is through these two computer programs. One is called Maps Windows GIS, which does the spatial work. MMP is the manure management planner, which starts to put together the nutrient piece of it from a crop production standpoint, and then has incorporated into it the P risk index as well as the nitrogen risk index, plus also you're doing erosion at the same time. It has the opportunity within MMP, and I want to look at those numbers with you, to do a P risk in two ways. It uses the current Ohio P risk index that Libby was describing, and then also provides another tool that's called the annual P loss estimator, which is called Apple. So it gives us a comparison, and we've been doing some nutrient management plans up in Northwest Ohio with some folks that work under me, and one thing that we've been doing is trying to look at these two tools and see what they give us as far as different outputs in relationship to understanding P loss. I think what we'd ultimately like to have is a map like you see here. The red fields have a high P risk index. Those are fields that we want to think about targeting in relationship to improved practices out on the field. The red areas that you see, and there's 20 fields on this particular farm, and there are 3 fields that had a high P index. And you'd have to go back and look at Libby's information to know what that actually is, but that's an area where we would start to limit phosphorus applications, no more than annual certainly, and relationship to management. I have 2 with a X in a white box, red X white box. Those are 2 that actually the P index did not come back with a high value, but the Apple tool did come up with a high loss. And we see that occasionally on the number of plans that we've done. Most times the P index and the Apple tool give us a very similar value, and we understand them, in relationship, but occasionally there's a low P index and a high apple value. And I think it's good to start looking at those fields too, just because there might be an additional risk that we need to identify. This is those fields with more detail behind them as far as what the P risk index is. First, let me just kind of go through. There's the 4 fields identified, and see if I can get this up. And these are the acres that are within those particular field boundaries. We have the 3 high P index fields. We have the apple output that came along with that. Somewhere right around 2.5 to 3 is what the loss in pounds per acre came out to be. And in all honesty, I really like the ideal of having it identified in pounds per acre, because I can start using that value here in a few minutes, I think, to make some better decisions in relationship to what we want to do. It does identify the risk source for us. It gives us the risk for field 1-4, which is that first field. It's related to soil test value. We have a 404 part per million Bray P1 test. When we start looking at the next 2 fields that are high, it's a combination of soil tests as well as non-vegetated surface inlets that we have in that field. When we start looking at the 2 last items, that's where we have the low P risk, but we are seeing where the apple output is giving us 2 to 3 pounds of loss, actually very comparable to what those high values are in relationship to looking at the nutrient management plan. So just so you know, when you look at the P risk index reports, you can get some detail behind, and this is actually the detail that's behind that first field. Where we have a high P risk index. The value is 30, and I know you can't see in the back, but it gives you all the values that was coming through from, the presentation from Libby. Gives you all those different values calculated out, and you can see that out of the 30, 28 points is coming from soil test value. When we put the apple tool to that, gives us losses, and there are really 3 sets of columns here. One is sediment and soil loss, then soil dissolved P, then what would be coming from manure, what would be coming from fertilizer applications, and then it gives us a loss value based off of without phosphorus application and then with phosphorus application. This is a high field, so the same values exist, and we're talking about 1.8 as far as pounds of loss in that first year based off the crop rotation information. This is that detailed report for the field that has really 2 variables that are coming into play. We're getting 16 points from the drainage and having surface drains that are non-vegetated, and then a P value that's coming back with 18 as far as the number. So 36 is the total P index, 18 coming from soil tests, and 16 coming then from the non-vegetated outlet. And we see those loss values then that we can use and come through the Apple program. I'm going to skip a couple more slides here, and you can get that same detail for all of those fields. And here's that field that we have that has a low P index, but actually coming back with values 2 out of the 3 years of 4 or greater, which, as you look back, most of it's coming from sediment loss in relationship to phosphorus loss. So what do we think about on different practices then? When we have high soil test levels, what are we going to think about as far as management practices? I would start thinking about cover crops to try and get more water infiltration, try and hold water back. You might think about drainage water management practices on that field where we're holding, can do the implementation of that practice and hold water back at certain times a year, reducing nutrient loss. It gives us a couple places to go with that. When we talk about the field with, surface flow concerns, what else should we think about as far as in the toolbox? Filter strips, buffers, grass waterways are one thing that I think we certainly want to implement, particularly if we have a sediment problem that's being tied back into the issue on that particular field. This is kind of a summary then of all those fields and the information from that, the high, the lows, the apple content. And what I think about doing is then taking that into a spreadsheet here where we start to calculate what is the total loss from any individual field. And right here you have the field numbers, those acres that we were originally looking at, those P-index values, but 11 acres at 2.27 pounds, that 11 acres is on an annual basis contributing 25 pounds of phosphorus to the problem. If we reduce that by half, what have we done? We've reduced it to 12 pounds, and we've made a progress there that looks good as a percentage compared to that 1.8 or 1.3 million pounds. It's in a small amount, but it starts to head us in the right direction. What else can you also ask about that value if you know what the actual loss is that you're able to prevent by implementing a practice? How many dollars per pound of loss are we actually able to do in implementing this practice on that particular field? And so that starts to me to tell the story about the overall economics that we need to think about in looking at best cost management practices or best practices that we can implement on a cost-effective basis so that we can answer, two things from this. The question of, are we making progress? Well, we made 12 pounds of progress towards that. And if it costs us $1,500 to do that, was that an annual cost or whatever, and it gives us a pound per, or a cost per pound of reduction that we can start thinking about in an overall economic picture. I want to, just to finish up, we don't always need a spreadsheet or piece of paper to tell us what is going on in the landscape. Is there a problem in this picture? Driving up between Marysville and this location in Ada today, I identified 12 to 15 fields that needed waterways in them, no doubt about it. And these kind of things are pretty readily seen in the landscape, that type of thing where we have surface water moving towards, really unfiltered surface water moving towards a direct outlet to a stream in essence. Does that need value put to it that we need to do something there? I think maybe we got a problem that we ought to address. And this is where we're starting to put together a best management fact sheet series, trying to identify critical resource concerns in a pictorial fashion so that people can start thinking about these and then looking at what best management practices they can implement so that they can start making things happen in the landscape without doing a lot of thinking about it. And that website that is coming online, actually you can go to it right now. It's a little less populated than we want it to be by the end of the month, but it's agbmps.osu.edu, and appreciate any feedback, input. There's a place to submit information on that.